Yeah. Alrighty, guys. Are there? We have a little bit of time before we get started. Are there any questions?
Hi, Professor.
Oh.
Do you have a date for when we'll take the oral exam, or the range of dates at least, please?
I don't have that here. It's going to be end of October.
Okay, thank you.
So if you look at the syllabus, there is a schedule at the end.
Mm-hmm.
And when we got through all that material, more or less, this is in the following week will be the week with midterms.
Okay, so do you expect it to be after October 20th or before?
Oh, I expect it to be after.
Okay, thank you. Sorry, I just have a schedule conflict.
Well, we will have, because it's going to be all, there'll be flexibility here to get it to work for students.
Thank you very much.
Are there other questions?
Oh, I have a question about the Lebesgue integral.
Yeah.
Do we have to know that prior to you teaching it, or are you going to teach from scratch?
You don't have to know it before. We're going to be talking about it tonight.
Okay.
There was a question about homework 2. Question number 2. Okay, let me pull up the homework formulation. Let's see. Question 2 in the homework. Alrighty, so what part of problem 2 are we not good on?
Oh, Professor, I did not know how to proceed with the first part. Never really used, I don't know what Laplace transform really is.
It's this one. It's this.
Yeah. Mm-hmm.
So okay, yeah, let me switch it over. So so you have a random variable x, which is exponential, with parameter alpha. Which is so what does that mean? This means if I'm looking at the probability that the random variable is what should we say, less than x, and I want to compute the derivative with respect to x, so I get the density. This is going to be alpha d to the minus alpha x. Okay, so then what you're asking for is you take a t that's positive and compute the expectation of minus t x. And in your probability course, you should have seen that these expectations, they can be computed as Riemann integrals. And the way you do it is you take this random variable in here. X is the random component, right? This is just a function. So when you have a function of a random variable, the way you compute expectations is by taking that function, replace the random variable with a dummy, so it's called little x. Then you integrate over where the random variable x takes values, and if x is exponential, it'll be non-negative, so it runs from 0 to infinity. And then you multiply onto the density, alpha e to the minus alpha x, and you integrate. So what this question asks you to do is to compute what this integral is.
Oh, okay. Thank you. Actually, I wasn't aware of this concept. I had never really done this before. So,
Okay.
thank you.
Yeah, this function here, so when you have a t between 0 and infinity, this map here, the map to t into this expectation, this is called a Laplace transform. Okay, this is a p Laplace. There was another question in the chat. Homework 2, question 2 and 3. Let's have a look at them. So these two here. Are we talking about these two questions? Are we talking about problem 2.2 and 2.3? Just 3. Okay, yeah. So I'm sorry. What part of it is that? What part of it is that we can't follow? Can the student tell me the one that has a question? Can we? You got to help me out here a little bit. What part is it that you want me to talk about in question 2.3? What is it? What's the confusing part again? Can you guys hear me?
Yeah, we can hear you.
Okay. What part of this question 2.3?
I think they're just asking if x and y have the same density. And
Yeah.
they do.
Do you have the same density? Right. So the density is the same for both x and y.
So is that mean they have the same density functions?
Yes.
So both is neither function fs equal alpha is less p.
Yeah. So if we take this as a definition of a density function, then I will write the same thing, but instead of the random variable x, I will write the random variable y. This is alpha e to the minus, oh, we should be using the same, so either little x here and little y there. Put x's, and we get this. Yeah, so these two have the same density. Equivalently, you have the same Laplace transform. So if you, there was one question about the Laplace transforms. If you haven't seen these transforms before, these Laplace transforms, like, so you work out what this one here is. This is something like alpha over t plus alpha. So so knowing the Laplace transform, this is the same. This is equivalent to knowing the density. Right. So for example, if y is a random variable, so it goes from omega, say, to 0 infinity. So if this one has Laplace transform, so you're given a random variable, it has Laplace transform, exactly what we computed up here. So if this is true for any t positive, so if you have a random variable, non-negative, you're told that it has a Laplace transform, this one. Well then, y's density is alpha to the e to the minus alpha x. So there is a one-to-one correspondence between, for example, the Laplace transform and the distribution of a random variable. Okay. Otherwise, I think maybe it's time to get. Are there any more questions on about this slide here or page here before I get started on today's material? And then we'll get started. So last time we last time we got started on measure theory. So last time we were quite interested in this omega f p. And I should say before we get started, where we're working now is in the thick book of our textbook, right? So it's number 2. Right? And where we are at in this thicker textbook is we are working here in we're working here in the first few sections, and then we're working down here in the first few sections in chapter 2. So we're going to be spending some time now working through chapter 1 and chapter 2 in this second book. But so last time we were interested in this. Right, so this here is our probability space. This one here, this is our sigma algebra. So remember what that means. Those 3 properties. So one was, here's a system of subsets of omega. The first property was that the whole space must be an element in there. The second one was that if I take a set in there, then that implies that the complement is also in there. And the third property was that if I take a sequence inside F, well then the union of that collection of sets is also an element in there. So that's what it means to be a sigma algebra. Beyond that, we haven't specified anything. And then the last one, this is the measure P. So P is a function, and it's a function. So this is our probability. This is our probability measure. And what that means is it has two properties, but it's something that goes from the domain is the sigma algebra, and the codomain is the interval 0 to 1. So it's a probability measure, and it satisfies two properties. The first one is that if I put in the entire space, I'm going to get 1. And the second one is that if I take a sequence, of sets, so this is going to be measurable sets in the sigma algebra, to satisfy that if I take the intersection, I get nothing. Right, so this is a sequence of disjoint sets. And for such a sequence of disjoint sets, if I compute the probability of the union of these Fs, this is going to be the same thing as summing the individual probabilities. So these are the three components. So beyond these properties, we are not saying anything about, we're not specifying what omega is. It's a collection of points, a collection of elements. If this is a system, it's a set of sets, it's a set of subsets of omega that satisfy these three properties. And finally, P over here, that's going to be our measure, and probability measure satisfy these two properties.
Professor, I have a question.
Yep.
What does that notation where you have like sets in a sequence mean? I'm a bit confused about.
This one?
Yeah, what is that? Yeah.
Well, I mean, when I write, so a sequence, so what is the meaning? What is the meaning of this?
Well, I think of a sequence as a function from n to r.
Right. Exactly. So this is a function from n to, if I write something like this, it's a sequence from n into r. Right. So then x of n, how is that defined? Well, this is x of n. So we can think about it that way. We can think about it as being just a humongous vector. I don't know if you have a preference for thinking about x as being either going this way or going that way, and of course also just write it like this.
Oh, and each of those are sets like x1, x2.
Yeah. So that's exactly the same thing. So you will have, it's a sequence of sets. So I will have that. So what do I mean by this? Or sometimes you'll see me write it as that, or I will write it as oh, this is not bold. So this is Fn and in the natural numbers, or I'll write it as F1, F2, and a bunch of dots. The only thing that means is that Fn belongs to F for any n in the natural numbers. Just as what does it mean for this sequence? So it means that I take an element here, I'll have that xn is an element in R for any n in the domain.
So the property is that the vector that has the sets is a subset of bold F.
This one? This just means, this is just an inclusion, right? This just means that each element in the sequence is a member of F. I can write here instead, I can write F1, F2, and so on with fn, and then instead of using this inclusion here, I'll write this.
Okay. Oh,
I'll say up here, if I write something like this, I'll write this as a subset of R. Or I will write that xn belongs to R for any n in the natural numbers.
why is the so I'm confused. Is it's you're kind of saying like the sequence is a subset of R?
Yes. But it is, right? Because if I write a vector, x is equal to 1, 2, 3, and so on, then if I look at the set 1, 2, 3, and
Okay,
so on,
the set instead of the vector. Okay.
okay, so this is the confusing part. Okay, so I am a bit, yeah, okay. Now I understand what the confusion is about. Yeah, I'm a bit liberal here when it comes to using these. So when I write something like this, I'm just thinking about the xn's as being a collection of points. So you can organize them as a vector, putting these parentheses, or I can organize them as being curly brackets. Yeah, yeah. This, yeah. You will. So in that way, this is something you'll see again. You will also not see me being very stringent about whether I'm writing x as a vector that goes this way or one that goes this way.
Gotcha.
The more important thing to keep track of here is, yeah, so now I hope we got that clarified. We're going to be working, what is in store for us is something that might make this even more confusing. So the next thing we're going to be looking at is something called a filtered probability space. So here we have a probability space. Now we're going to get so then there's a new word here, filter. A filtered probability space. What that means is that you have a sequence. You have a sequence of sigma algebras. So now we're going to have fn, where I'm indexing them, say by n. So it becomes now important to separate out. Up here, the sigma algebra doesn't have, there's no n here. Whereas the sets that are living inside, when I'm doing this union, they will be indexed. Well, we're going to get a filtered probability space, and this is going to then involve a sequence of sigma algebras. So now, a sequence of sigma algebras, what is that? Well, it means that each element in the sequence is a sigma algebra. So each, maybe it's not good to call it fn, maybe I should call it fm here. So each fm is a sigma algebra, so each fm satisfies these properties. And then I'll have, on top of that, I'll then have this index here. And then I'll have that these things are ordered such that fm is a subset of fm plus 1. So they grow. So this is, that's how far we need to take it. So right now we have a probability space. The next thing to talk about martingales, for example, we'll need this filter probability space. So then there'll be another index to keep track of. There'll be another index here. Okay, so just, yeah, that was a little side comment. This is coming, maybe not today, but it's going to be in store for us soon. A filter probability space. So then we'll have omega fp, and we'll have the sequence of fm's going around. Okay. Are there more questions before we continue? So this is pretty abstract, but we're putting very little structure on what we're dealing with here. One thing to note is that I am indexing here. I'm indexing here by the natural numbers. So that's important. We are indexing by natural numbers. We're not indexing by like the rational. We're not indexing by the real numbers. these here are countable. You're countable. Yeah. So for those of you that are familiar with it, so what does it mean to be countable? Well, I mean, you can count them. So if you have a set, you will say that this set is countable if you can find a map between the set and the natural numbers such that the map is one-to-one and onto. Okay, so let me maybe say that something like this. So countability. So it's important. So one should note we index by n. So this is countability. And if you haven't seen countability before, this is not really a class where we teach what it means to be countable, but just maybe to give you an idea about it. Like there are sets out there that are not indexed necessarily by natural numbers, but you could look at something like Q, like the rationals. So the rationals, those are the ones that are given as ratios, P divided by Q. Say for, if I take the positive ones, so take the positive ones, so I have P and Q, say, in N. So I'm looking at these ratios. So how would I prove that the set of positive rationals would be countable?
Draw the grid and do that snake thing.
Very good. So you've seen this before. Okay, that's awesome. So we do 1, 2, like I put the natural numbers out here on like this, and I go down here. So the first one, this is 1 divided by 1. Okay, so then I go 1 to the right. So this is 2 divided by 1. So I'm interested in creating a mapping if that goes from n into Q, say Q plus, and I want this map to be a bijection, right? So it's 1-to-1 and onto. And so how would I do it? Well, I would send this first number here, the one up here in the corner. That's going to be my first one. That's a 1. And then I move 1 to the right. So I'm going to map 2 into this one. And then, as being suggested, I snake it. So here, this will be 1 divided by 2. That's going to be my number 3. I scooch 1 over. Maybe I already had that one. 2 divided by 2, this is 1, this is the same, so then I scooch up here. This is 3 divided by 1. And this will be 3. And so on. And then you scooch back, or you go over, and keep going like this. And this is how you get your map created. You fill this thing out, and you then prove that this map is onto, and it's invertible, and then you prove that there are just as many elements in the sense that you can create this map in Q plus as there is in N. So we could also index by the natural numbers. And we could also, instead of the natural numbers, index by Q plus. And so, of course, you could also ask yourself, so what is not countable? Okay, so then you could take a number. You could take a number like, so index by n. So this one here was also countable. However, if I look at, say, the set 0, 1, this is not countable. So we're claiming that we can't do this trick with this f up here if I were to put 0, 1 over here instead of Q plus. Is this something that you guys, some of you have seen before? There's a famous argument for this one.
Enters, diagonalize it, yeah.
Yeah, very nice. So this is really taking us a little bit. This is really taking us a little bit off here. this is pretty cool. Canvas diagonalization argument. So if you're interested in things like this, try to look up canvas diagonalization argument. And that will give you that you cannot create such a map up here. It's not possible. I don't know what class this. I taught a class 300 at some point. We were playing with this stuff there in the end. You can get into the, you can start asking yourself, okay, so now apparently I have more elements here than I have up here. Okay, so can I create something that has even more elements than this one? And so how would that set look like? And so on and so forth. And so then you get all these cardinals. Yeah. This is going to take us too far away from quantitative finance. What we're having here is we have only the ability to do countable unions here. And that's important to remember. When you do mesh and integration theory, stuff has to be countable. You cannot deal with these uncountable structures. So there is the friction that comes in here, and this is always colliding in this theory, because some of you might have been in a class where you talked about topology. So this if you've been in a class where you talk about topology, there is a difference there. So then you'll have this is again going to be some system, tau. It's going to satisfy some properties, but one of the properties that tau has is that if my f t is running through tau or some subset tau prime for any subset so if I have a topology, then put this inside T for any subset T or for any set T. I'll take so now I'll not call this a sequence anymore. I'll take a collection of sets ft T running through some capital T set with if T being an element in the topology. Then this is different, because then you're going to demand, if this is to be a topology, you're going to demand that if I can take arbitrary unions have to be elements in the topology. So this is different. This thing here has to work for all kind of unions, not just countable unions. So there's going to be a friction between this mesh and integration theory, because there you're restricting attention to countability. But for something like topology, if you want to have a collection of sets that's a topology, well, then you need to have this property. And you need to have other properties too to be a topology, but in particular, this one here is the one that highlights that there is a clear difference between topology and the set algebra. For those of you, and also if you move on, if you go into grad school, if you're taking a PhD level course in mesh and integration, this here is going to become a real troublemaker. And so why not allow for why not follow suit and demand that P satisfies? Why not follow suit and demand that P satisfies that if I take P of an arbitrary union, so let me continue with this index here, T and T of my FTs, that this is the same thing as summing up the individual ones, where I'm going to have that my union is an element in F. I'm going to have that Ft is an element in F. And I'm going to have that ft intersection with ft prime. This is mt for all t that are not the same as ft prime, right? So what I'm doing is I'm just copying the condition I have here, but instead of having a countable structure, I'm now allowing for an arbitrary structure. And then I'm claiming that this works well in topology, so why not just do the same thing here? Why not do this? Well, let's look at an example. And this goes back, we can use the example we had in the very first few minutes of tonight's lecture, right? We were playing with the exponential. Okay, so the exponential is a random variable that takes positive values. And it has this density. So then, if I'm looking at, if I take such a random variable, so I take x, goes from omega into 0 to infinity, exponential. What could my ft's look like? Well, I could say that ft, this is going to be, what is it going to be? This is going to be where x is equal to t. Yeah, so this is where my exponential random variable takes the value t, and this is for a positive number. So then I'm going to have the structure over here. I'm going to have that whenever I intersect two different values of t, these two sets here are going to be independent because x cannot both take the value if t is equal to 1 and t prime is equal to 2. It cannot take the value 1 and 2 at the same time. So these are going to be disjoint. It's going to be the case that the union, what's the union of all the FTs?
One.
Not one. The union of all the FTs is going to be everything, right? There's no probability here. But what I'm doing here is I'm looking at this is my omega, and I'm slicing in bits and pieces. This here is where x is equal to 1. This here is where x is equal to a half. This here is where x is equal to, I don't know, a third, and so on. So when I take the union of all possible values of t, I'm going to get omega.
Oh, okay. It's not the probability of.
There's no probability yet, right? But now we do the one, right? Because if I compute what is the probability of the union, the probability of omega, well, that's going to be 1. But what happens if I take the sum of the probabilities of the individual ones? Well, what's the probability of an exponential being equal to a specific value?
0.
0, right? So then I have a bunch of zeros. And on the left-hand side, I have a 1. That doesn't work. Right? But P of omega is equal to 1, whereas if I look at the sum of P of Ft, I'm going to get 0. So this is why we're not following suit. We cannot do this. It won't work. So when we work with probabilities, this here is too much. And so there's an interesting debate going back many years about how one should set this up. Because people would, right, so we have people that think that topologies, this is the way to go with things in life. And then you're having people that were like, we want to do integration. And these two things don't mesh very well. And here's an example of why does it not work so well together. You can get some things to work, but you cannot get stuff like this here to work. It is way, way, way too much to demand that you can take arbitrary disjoint unions and hope for your probability to work like that. Okay, are there more questions on? So this is just a a little bit about what we did last time, maybe some comments about why we're doing things the way we're doing and what does not work. Any questions or comments on what we've done here? Otherwise, we're going to shift gears and maybe start talking a little bit about integration.
So the explanation you did entirely right now proves that we need to have a countable set.
At most.
At most. Okay.
At most, right? We can always go the other way. The other way is not nearly as bad. If you wanted to lower, make it simpler, then this is okay, because say that I got this thing to work for countably many. You can from this one you can quite easily get that this year is stronger, and it's strictly stronger than demanding something like a finite union. You can quite easily get from the one you have up here down to the one you have here. And the reason is that you simply just set Fn plus, you set Fn equal to the empty set for n bigger than capital N. Because then when I take union with empty sets, I'm not going to destroy anything. And the probability of the empty set, because the probability of the full set is 1, there's no space left. The probability of the empty set has to be 0. So I'm not adding anything on the right hand side when I go from capital N up to infinity. So you can at most do countable here, but you can do less. It's okay to just do a finite union, just do 2 elements. That's okay. But we cannot get carried away and start putting in I run n through like the interval 0 to 1. This will never work. Okay, so that being said, our next goal is to do Lebesgue integration. So Lebesgue integration. So our goal is to give a precise meaning to this thing here, Ex. And this here can be written in many different forms. Now it's just a question of notation. So what I'm writing here does not have any mathematical meaning. It's just different ways of writing this expectation. This here is the same. The notation is the same as writing an integral over omega of x, and then you write dp. And this is the same as giving meaning to writing an integral over omega, and then you can write x of little omega. You can write this here as dp of omega. You can write this here as the same as x of omega, and some people write this as p of d omega. All these 4 symbols do you use interchangeably. They're all just different ways of writing the same object. There's no math here. This is just notation. In other words, there's no difference between writing what's written here and writing this one, writing that one, or writing this one. You can write whichever one you want. And as you can see here, this is x and then dp. So it's a little bit confusing. It can be confusing. Can be confusing to integrate to denote by x the function. This is what we'll call a random variable in a little bit. So you often in calculus you write f of x. So you write this, but we write x of omega. And so it can be confusing that this little x here is a dummy variable in calculus, whereas for us the dummy variable is this omega. And before you blame me for this, this is how textbooks write it. This is, and this includes the textbook that we're using. So, okay, so this is our goal. How do we give meaning to this? And of course, you guys have seen how to integrate here with respect to dx. Right? You already did it in the homework, right? You've been integrating this f of x with respect to dx. But this is not what we're writing here, right? This is not dx here. This is dp. This is an integration. This is integration with respect to that probability measure that we had, that we've been talking about. Like this is with respect to this measure here. So this is not going to be the integral that you have seen in calculus. Indeed, this is going to become the Lebesgue integral. Okay, so are we ready? How do we do this? Well, just briefly, let me remind you how did you do? So in calculus, you looked at an integral, say from 0 to 1 of some function with respect to dx. And the way that you did it was, you plotted the function f. So this is my f. I have my x down here. And how would we compute this? Well, you look at sums. So you look at lower sums and upper sums. And so what you would do is you put in, say, squares. Put in a square here. And then you go up here, put in a square, put in a square. And so on. So what you do is you would split the x-axis. So you have x0, you have x1, x2. And so you would have like a delta x in there. And so you look at the height. You look at something like f of x0. There'll be another height up here, f of x1, and so on. And then you would ultimately look at this integral here as some sort of a limit as your delta x would go to 0 of sums. You sum up the finitely many rectangles, you will fill up. If this here is if this is 0, and then I'll go up to say xn, which is 1. You will fill up the space between x0 and out to 1 with these rectangles. We try to approximate them as we did here. So if you have f of x, say k, right, and then you multiply onto, that's the height, and then you would multiply onto the width, which is my delta x, and then you will be summing over a bunch of k's. You have hopefully seen something like this, that the area underneath the curve f, and this is what is meant by this interval from 0 to 1 of f of x. But of course, when you turned around and you actually started doing intervals, you started calculating what these intervals were, you would not go back and look at these Riemann sums and then compute those limits, but you would have the fundamental theorem of calculus that would allow you to figure out how to compute many of these intervals. You would not go back to the very definition of the Riemann integral and try to compute the limit of these sums. Like to prove the fundamental theorem of calculus, then you would need the sums, but given that you had done that, you would instead start looking for other functions that would have little f as their derivatives, and then you use those to figure out what these integrals were. So the important thing here is that when you did the Riemann integral, I guess here's Riemann. Always again, 1 or 2 minutes. Riemann, when you did the Riemann integral, you split the x-axis. You split the x-axis. Right, and the x's, those are the ones that we integrate over. So for us, we're integrating over omega. So omega is the thing that varies. Here, x is the thing that varies. X varies between 0 and 1. Here is my little omega that varies inside capital omega. So for us, we integrate over omega. But how do we split? How to split omega? Like it was easy here because you were looking at the interval. You were looking at the interval 0 to 1. So how do you split the interval 0 to 1? Well, you throw in a bunch of points equally distanced delta x. But how do you split omega? So that is just a problem. We don't. So Lebesgue's idea. So the idea behind the Lebesgue integral is to split. So here we're talking about domains. This is the domain. The interval 0 to 1, this is the domain of f. Omega, this is the domain. This is the domain of x, right? Those are the elements that we can feed into x and get numbers out. And this is what we don't know how to split. So the idea behind the Lebesgue integral is not to split the domain, but to split the codomain. So this is the range of the image, range, whatever you want to call it. So instead of splitting here on the x-axis, we split up on the y-axis. Okay, so that's the idea. Now, how do we do that? And this is going to take us a little while to do, but we should be able to do that tonight. Before I move on, are there the question is this high level? Yeah, go ahead.
So since we're splitting along the y-axis, isn't that directly obtained from the x-axis? As in, like, I know you said the codomain, but isn't that also like a function relying on the x-axis or not?
So we do not know whether or not there's a one-to-one relationship between
Oh, okay.
the x-axis and the y-axis. Even here for the Riemann interval, this is not the case, right? There are, if I put a flat line, right? If I put a flat line here, see if I can get it to work. Like I can find there's one x there, there's one x there, and there's one x there. I can find three x's that give me one y value. So that is not, it's not going to be this simple. And in our case, when omega can be really complicated, remember the examples we had last time of omega, like omega could be a set of functions. Right? So an element inside omega could be a continuous function that's 0 at 0. So that is not, that's not how easy it is. It's not going to be that easy.
Okay, thanks.
Yep. Okay, so here comes the Lec integral. The Lec integral. So we're gonna need some prep here. So the first thing is a random variable. What is that? So a function. So this is my x that goes from omega into, say, r. A function is called and this is the word, random variable if what? If the set x less than or equal to a, so this is my notation. This is like a shorthand notation for those omegas in the domain such that when I feed them into x, when I take something in the domain, plug it into x, I'm going to get something in the codomain. Right, so this is something in R. When this is less than a, right, it's just a bit long to write this all the time. This here is a bit shorter. If this set here belongs to F for any a in the codomain, so a function is called a random variable if it satisfies this property. Random variables are also called, and instead of calling them functions, you call them measurable functions. So probabilists call measurable functions for random variables. And, yeah, so I'll call them random variables. Those are functions that satisfy a very particular property. It has to be that this set here is inside F. And you can see it, right? This is just a note. When we talk about X's distribution, what do we talk about? We talk about the probability that X is less than A. What sets am I allowed to plug into P? Well, I'm allowed to plug stuff into P that's in P's domain, otherwise I'm not allowed to do it. Right? So P's domain is F. So for me to write the probability that X is less than A, I must have that set X less than A is something in F. So X's distribution, this thing, requires that X is measurable.
Right, so really we're saying like X of the omega is less than A.
Well, it's those omegas. It's those omegas where X is less than A. Like how?
Okay, so X maps omega into F, no, into R,
Into
into
R.
R, and then that
Yeah, x is a function that has its domain is omega. So that means that you can take things inside omega, plug them into x, and it spits something out in the codomain. The codomain here is R. So that's my x. Okay, so now I want to talk about x's distribution. Well, the way that you have seen the distribution before is the probability that a random variable is less than some dummy, some constant. Okay, so that, just to talk about that, I need to be able to plug this set here. I need to be able to insert this set here into P. But that requires that this set here must be in P's domain. Okay, but P's domain is F. So that means that this set here has to be in F for this expression to make sense. Right, this is X's distribution. This is this map that maps A, and A is something in the codomain of R. It maps A into this probability. That's called X's distribution. Right? And so if you look at it on a picture, what are the probability? What are the properties of a distribution function? Well, when A is close to negative infinity, this probability here is small. Okay, so you're going to get something that will look like it'll decay over here to 0, right? And then it's going to run. It might have jumps. It's going to be increasing. It might be flat, but it'll increase. It can increase, and then ultimately it gets up to be closer to 1. So this could be. This is an example of a distribution function. Towards the negative infinity part, it dies off to 0, and towards plus infinity, so this when A gets to be very big, probability that the random variable is less than something very big, this is something that's going to go closer to 1. And then in between, it can have jumps. It's non-decreasing, and in between, it can have jumps. That's a distribution function. Okay, so we have a random variable. So on the other hand, if x is any function, on the other hand, if x is any function, so x always goes from omega to R, we denote by, again, this sigma of x. So remember that letter sigma, it signifies something about the sigma algebra. Last time we looked at sigma of A, and that was the sigma algebra generated by a set A. Now we're denoting by sigma of x. This is the smallest sigma algebra, such that this property of your holds, such that x less than A belongs to the sigma of x for any A where and x is codomain. So when you see this sigma of x, this means it's a sigma algebra. It's a sigma algebra that has the property that x is measurable with respect to it, and it's the smallest such sigma algebra. So for us, so very often in our class, what we have is we have a sequence of random variables. So we have say xn, maybe an infinite sequence of random variables. So xn goes from omega into r. So we say, so then we look at fn. Then fn, this is going to be the sigma algebra generated by x1, x2, up to xn. This is, then this guy is, denotes the smallest sigma algebra such that each one of these x's is measurable. So such that xk less than a belongs to fn for any a in R and for any k between 1 and n. So that's our filtration. So here we note, if I look at F1, this is the smallest sigma algebra that makes x1 measurable. F2, this is the smallest sigma algebra that makes x1 as well as x2 measurable. Which one is biggest? Which one is smallest? Well, the second one has the property. The second one has the property that both x1 and x2 are measurable, whereas f1 has the property that only x1 is measurable. So this one here is bigger than that one here. So we have the inclusion. And then this keeps going all the way up. You get bigger and bigger and bigger. And this the n down here for us is going to be time. So this is our model. This will be our model for the flow of information. Okay, what on earth does that mean? Well, what is it we have in mind? Let's see if I can get this to work. So what is it we have in mind? So we have a binomial tree structure in mind. We have a binomial tree structure in mind. So what is a binomial tree structure? I want to have, so my x1, so we have n equal to 0, n equal to 1, n equal to 2. So I'll have x1, I want to think about this is the first flip, and x2, this is the second flip. So I have 4 elements in my omega. So I have omega is equal to heads, heads, so heads, heads, is equal to heads, tails, heads, tails, is equal to tails, heads, is equal to tails, tails. Okay. Are we all good so far? This is the 2-period binomial model. So what's our goal? And if you say we start out at S0, it goes to S0 U, it goes to S0 U, so this is U, U, S0 U D, S0 DU, S0 DD. This is S0 D. That was the one we talked about last time. So what are these sigma algebras we're looking at up here? So F1, what is the smallest sigma algebra? What's the smallest sigma algebra that makes X1 measurable? So I need sets here. This here is a subset. This contains subsets of omega. What subsets? Well, I need to look at sets where x1 is less than a. So what will I be able to say if I know? So I have S0U, I have set S0D. Maybe we should put some values here. If we say that this is, if we say that this is 4, we say that this one here is 8, we say that this is 2. And then the next one up, we say it's 4, 8, so what was it, 16, 4, 8, 4, 8, 4, 4, 2, and then 4, and this is 1. So I need to figure out what is the smallest collection of subsets that contain all of these. So let's try to work out some examples. If I take, and I need to look at these sets, right? So let's take A equal to 10. Take A equal to 10. What is the set x1 less than or equal to 10? What points in my omega will give me a value of x1 that is less than 10? Well, x1, okay, so this here is my x1, so this is 8.
Is it all of them except HH?
Well, HH is going to give me...
I mean all of them except HH.
No, keep in mind here, so here is where I'll find my x1s.
Oh, but the omega is
So maybe
two outcomes.
Maybe I should call, yeah, maybe this is confusing. So this is x1, this is, so I should say here, this is after the first flip, and x2, this is after the second flip, right? So you flip the coin once, and x1 is going to be 8, or x1 is going to be 2. I flip it 2 times, it'll go from, either if it's up here, it'll go to 16, or go down to 8, and then the same thing in the bottom part here. So x1, this is the value after the first coin flip. So if I'm looking at what omegas will give me, what omegas belongs to the set when x1 is less than 10. Well, x1 is either going to be 8 or 2. So what omegas will it work for?
H and T.
Well, omega consists of HH, HT, TH, and TT.
All of them?
All of them. Okay, so then if I look at x1, when do I start getting some action? When do I start getting some action here? What should I pick for A to get some action?
7.
7. If I pick A to be 7, what do I get now? What points in my omega space can I feed into x1 if I want to get a value that is less than or equal to 7?
Just T.
You cannot. There's no just T.
There's no TH or TT.
So T what? Sorry, say it again.
TH or TT.
And TT.
And
Right, right, they have both of them in here.
okay, I see. So if it goes to 8 and 1 and then goes back to 4 and another 1, doesn't count. Oh, it's time 1. Okay, I see.
And so the last, so where else do we get some action? If I take x1 to be less than what? What should I pick for a here? Very good. I can see it now out in the log. Yeah, Shim's right. What about if I picked minus 10? Right, I have to get this thing to work. I have to get this thing to work for all A, not just like these specific ones. These are just like practice ones. So what do I get? What do I get if I am? What do I get if I am less than? If A is equal to minus 10?
Null set.
No. We have not talked about null sets. We get the what set? We get the empty set.
Oh, they're not the same thing?
No. Null sets, we will get there. Null sets, a specific null set is the empty set, but there are many other null sets. Okay, so what's my small sigma now? I need to have these sets in there. Okay, so I'll put in omega. I'll put in TH, and I'll put in TT. I'll put in the empty set. What else should I put in there? Well, it has to be a sigma.
The complement of the TH and TT.
Very good. So we look at the complement. That's going to be something over here in H, 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 T. So that was my sigma of x1. Now what's going to happen with sigma of x2? Oh, not x2, sorry. Sigma of x1 and x2. Well, now in addition, I also have to make x2 measurable. So I need to make x1 measurable, and I need to make x2 measurable. Any guesses on what we're going to get out of this? So now we pretend we know. So we need to go through this exercise one more time. But
It says it's a sigma algebra. Do you know it has to have omega in it?
it always has to have omega in it.
Right. So we can put that and.
We also, I mean, so we know that inside here we got to put all that stuff. We got to put all that stuff in there. What else are we going to put in there? We need more. We need to make x2 measurable as well. What do I get when I start making x2 measurable?
So is it like if you were to do less than or equal to 4, you would get HT, TH, TT as one subset?
So let's look at it. If I look at x2 less than what number do you want to put in? So should we start out with what should we start out with? Like a 16? X2 less than 16, we're going to get everything. If I look at x h2 less than what? Which one was it? 4?
Yeah.
Yeah. What are we gonna get here?
HTTHTT.
HTT. Being sloppy here. HTTHTT.
Yeah.
Yeah. And then you want to do x 2. You want to do x1 less than no x2 less than what? 3. What do we get here?
Just TT.
TT.
Then we take their complements. To,
Let's just run through it. And so if I take x2 to be less than what? Minus 10, I'm going to get the empty set. We have to have all these sets. We have to have all these sets in the sigma algebra 2. So I'm going to start adding now. So we already had omega. He was there. We don't need to put him again. Then we have to put this one. HT, TH, TT. And we have to put TT. Is that a sigma algebra?
we need the complements.
We need the complements, and we also need to be stable under unions, intersections, and differences, right?
Yeah.
Okay, so let's do differences first. I have TT here, I have TH and TT, so I need to have the property that if I take that set minus this set, it has to be in there. That's TH. So I can do the same thing with this set over here. It has to be the case that I can subtract away these two sets. Okay, so then I'm going to get TT goes away, TH goes away, I get HT. Okay, but then I take this set up here, it has to be stable under subtraction. So this set here minus HT is going to give me HH. Okay, is it the sigma algebra now? Yeah, not quite, right? Because you also have to have all the unions have to be in here. And I have one union here. I should also have, gosh, I need to be able to unionize these 3. So it'll be TT, TH.
Is this going to end up being the power set?
Okay, so now we're there, huh? Now we're there. And I'm also running out of paper. This here is going to be 2 to the omega. Shin, you're right. This is everything. And there was a question here that if 1 is bigger. No, if 1 is not bigger. No, if 1 is not bigger. If 1 makes x1 measurable, if 2 makes x1 and x2 measurable.
I have a question. When we say and, usually I think of like both of them being satisfied. It kind of feels like or to me here for some reason.
Which one?
For F2, when we say like it makes F1 measurable and F2 measurable.
Yes.
Like are we saying that we have at the x1 less than or equal to a and x2 less than or equal to a at the same time? So I'm a little confused.
No. This is so the definition is that this sigma algebra here has the property that when I'm looking at sets where x1 is less than a, all those sets they belong in here.
Oh,
Furthermore,
so you consider them separately when you
one at a time, right?
okay, one at a time. Yeah.
This is important because, yeah, we do not consider them at the same time. This is a recipe for disaster. this definition here that we're talking about. Remember how we had a discussion about countability? So when we do Brownian motion, this here is going to come up in continuous time. The following comes up. And it's clear that it's going to come up in continuous time because here, these indices is 1 and 2 here. It is related to time. Right, so in discrete time, we have countably many time points, but in continuous time, we have infinitely many. So in continuous time, the following issue comes up. I will have xt, but I'll denote the index by I'll denote this here by the positive numbers because this is going to be my time. Right, so what is sigma? What is the sigma algebra generated by xt when t runs between 0 and infinity? And this is the smallest sigma algebra such that xt less than a belongs to this sigma xt, t runs between 0 and infinity for any t between 0 and infinity and for any a in R. So we do not do them simultaneously. We do one at a time.
So when you have xt less than a is an element of that sigma, that means it's measurable.
Yes.
That means it's been made measurable.
Yeah, but it's been made in sigma algebra. Here it's not, you have to have a smallness property too. It is not just any sigma algebra, right? Because how could, if I'm only requiring measurability, then why does sigma x1, why does it look the way that it does? Why isn't that sigma x1 the same thing as sigma x1 comma sigma x2? Because both these sigma algebras have the property that x1 is measurable with respect to it. You also need the smallness property. This one here is the smallest sigma algebra that makes x1 measurable. Right? Because both this one here and that one here, both of them make x1 measurable. But this one here is much smaller. So it's not enough just to say that it's measurable. You need to have the smallness property. This is the smallest sigma algebra that has this measurability property.
And the sigma algebra is a collection of subsets of the probability space?
Yes. Yes. Right, this is what we have here. Omega fp. F is a collection of subsets of omega that satisfy properties 1, 2, and 3. Okay, guys, we got a little bit away with this example here. We will pick it up again. Next time. I have gotten an email from the administration saying that the way that we are accessing Zoom has to change. I am not quite sure yet how this is going to work. It said something like we have to use passcodes now. I'm going to try to figure this out. We have a few days to figure this out, but there will be either emails or announcements on how to get this to work. I'm just giving you guys heads up that something is going to change with Zoom. There seems to have been a problem with people getting into Zoom lectures that don't belong in the class, and then they make a problem for the class and the professor and so on. So they want to increase like the level of difficulty in getting into these lectures. I'm going to try to figure out what's going on, and then you'll get an email or there'll be an announcement on Canvas about this. I'm just telling you what's coming up. And then tomorrow morning we have office hours. Okay. Otherwise, it's time for me to get something to eat, and have a good night, guys.